Welcome back to another AP Pre-Calc lesson. We're now looking at 1.4 polynomial functions and rates of change. So now the big thing is looking at polynomials and figuring out what that means. One thing we did in class is just define a polynomial. Realize a polynomial is basically a combination of coefficients. Remember, coefficients are numbers in front of variables. And then you have your variables, obviously, and you have your exponents. Realize those exponents have to be whole numbers, so they can't be negative and they can't be decimals or fractions. That creates other types of functions that we'll start to explore later this year. So if you want an example of a polynomial, you have a number in front of your x, you have some exponent on that x, and you can just have a bunch of different terms. It doesn't matter if the values, the coefficients are positive or negative. Doesn't matter if your exponents are even or odd, nothing like that. You might even have a constant, which is just a number. Okay, that's an example of a polynomial. One thing we need to understand is degree. Degree of your polynomial is simply the largest exponent. The largest exponent in this case is from this term where the exponent or the degree is 8. Your leading coefficient then, you might abbreviate that as LC, is the number in front of that term. So the largest exponent, you look for that first, that's your degree. And then your leading coefficient is just the coefficient, the number in front of your x there, so that'd be 2. One thing you can also talk about is just your leading term, which we just kind of broke that down. Your leading term here is 2x to the 8th. Okay, so that's just basics about polynomials. Polynomials have graphs that generally look like this. They don't necessarily have these endpoints that we're looking at unless you restrict the domain for some reason. But polynomials, their graphs will never go above part of their own line. They move from left to right, just going up or down and never working back at all. So let's start to look at this then. Two things that we talked about is relative min and relative max. Well, remember, a minimum and a maximum are the highest and lowest points on your graph. The way that we defined that in this class is it's where your function goes from increasing then to decreasing, right? It went up for a while and now it's going to go back down. You could also have the opposite of that, right? Your graph might have been going down, but it changes to then go up. Your minimum and your max are those high and low points where it changes from increasing or decreasing. Okay? Endpoints can also be considered relative min and max as long as it doesn't have an arrow on one side, right? So we have an arrow here. That is not a minimum or maximum. But we do have an endpoint over here that would be included in our list of minimums and maximums. If you talk about a relative min or a relative max, you're simply talking about all of the places where there is a minimum, all the low points, or where there is a maximum, all of the high spots. Well, let's look at that for these two examples. Let's look at our minimums and our maximums. We have minimums on this first graph, way down here, right? Our graph was going down, it was decreasing, it changes to increase. Notice your graph increases, and then there is no other spot where it will change from decreasing to increasing. So the only minimum we have is at x equals -2. Okay, we reference these by talking about the x values. Relative max, find those spots where it goes from increasing to decreasing, right? It turns around at the top. That would be up here. That's at the x value of 3. But okay, we also said we had an endpoint over here. That endpoint does get included. So there is another relative maximum at x equals -4. From there, we need to look at the absolute maximums and absolute minimums. Well, that just means which one is the highest, which one is the lowest. Well, the absolute minimum, you only had one relative minimum, so it has to be that same spot. And your absolute maximum, there was 2 of them, so which one is higher? Well, if you look at both of them, this one looks like it's at 2, this one looks like it's at 1. So you know that the maximum occurs at 3. One thing you might include with the absolute min and max is what is the actual value. For example, if I talk about the absolute max, the maximum is a value of 2, which occurs at x equals 3. So you can talk about what the actual maximum is, what is the highest spot it reaches, as well as where it occurs, which is when you reference the x value. Same idea for minimums. We did that same process with this one as well. Again, look at the endpoints. Those do count. So just list each of those out for your minimums and your maximums and see if you would get the same thing. So my minimums, I get an x value of -3. I get an x value of +3. My minimums, again, just list all of them for relative min and max. My maximums, then I see -4 for an x value. I see 0 for an x value, and I also see +5. Both of those endpoints were points. They were not arrows, so they do count. So then start to talk about your absolute minimum. Well, the absolute minimum now of our graph, the very bottom of our graph, is at -3. But where does it occur? So the minimum is -3, and it occurs at the x value of -3 as well. The absolute maximum was this endpoint on the right side, where the max point that we got was 4. But again, talk about where it occurs as well. In this case, it occurs at the x value of 5. Okay, so different ideas you can talk about there. Where it's occurring, you can talk about the actual heights of those maximums and minimums, different things like that. From there, we discussed fun facts about polynomials. These are just ideas that we're going to learn throughout the year. One idea is between two real zeros. Realize a 0 is an x-intercept. That's one way we can define a 0. But between two x-intercepts, or two real zeros of a polynomial, there must be at least one relative min or max. Let's talk about that. If I have a graph, I have two zeros, two x-intercepts. Oops, go away. Okay, I have two x-intercepts, so there's one of them. Let's say there's another. Well, if I go through the x-axis, then I have to then circle back to reach that other endpoint. So that tells me I must have a maximum or minimum in between, right? Because you have to come back around to it, that does exist. There's other examples that you might look at depending on your multiplicity of those x-intercepts, but that's the basic idea. We'll just start there. The other fun fact we learned is polynomials of even degree will have either an absolute min or an absolute max. That's an idea we're going to talk a lot more about in 1.5 and 1.6 when we start talking about end behavior and stuff like that. But even degree, one thing you're going to learn in those sections is even degree polynomials, the ends always go in the same direction. For example, a parabola, an x squared graph. Well, if your ends go in the same direction, they will go up or they'll both go down forever. Then there has to be a spot that is the highest or is the lowest for everything. Okay, so that does tell us a little bit more information there. From there, we can continue to talk about some of these other things. For example, a point of inflection is the other thing we talk about. A point of inflection occurs when a function changes from concave up to concave down, or the opposite. But the idea we need to really understand is, okay, but we're talking about concavity. So what is our definition for concavity? Well, concavity, we always talk about rates of change. Something is concave up when your rate of change is increasing, and it's concave down when your rate of change of the function is decreasing. So if we're looking at a table or some function values, you would know that there's a point of inflection when the rate of change changes from increasing to decreasing. We'll start to see a lot of examples of rate of change built in throughout this entire course. That's one of the main things we need to understand. But if all we're trying to do is just find the different points of inflection on this graph, just look at the concavity, right? Now your graph is concave up, but oh wait, it starts to flip. Now notice it's concave down. So that tells me there must be a point of inflection right there. But okay, as your graph was decreasing, now the rate of change is slowing down and turning the other direction, so it must be increasing now. So there must be another point of inflection. So 2 points of inflection in this case, one at -1 and one at +1 for the x values. Again, the reason we know that is it changes from increasing, from concave up to concave down or vice versa. Okay, there are some examples for you. Hopefully that helps. That's lesson 1.4.